Hello. In this video, we're going to be covering over the topic 3-1, any of the notes in there. This topic is primarily dealing with the periodic table and its design. So without further ado, let's go ahead and get started. So just a quick history of the periodic table. The very first periodic table was developed by Dmitry Mendeleev, a Russian scientist, in the late 1800s, early 1900s. And when he developed his periodic table, you can see it right here on the left, he made his by an order of increasing atomic mass. Now, during this time, not all elements had been discovered, but Mendeleev was so intuitive that he left spaces on his periodic table where he believed that they would eventually discover new elements, and those elements would be in those locations. In fact, he was even able to accurately predict those properties that those undiscovered elements would have. A few years later, we have Henry Moseley. He decided to rearrange the periodic table a little bit differently, this time by increasing atomic number, the one that we use today. And the reason why we still use it today is because when we have these elements by increasing atomic number, we exhibit what we see known as periodic law. You see, if elements are grouped together in order of increasing atomic number, certain patterns start to periodically emerge from the periodic table itself. Elements, for example, in the same column will exhibit similar chemical and physical characteristics. And so that's why we still use this periodic table today. So that's periodic law, developed by Henry Moseley by rearranging the periodic table by increasing atomic number rather than atomic mass, developed by Mendeleev. Now, a couple of things that you need to know based on the elements of the periodic table is this particular demonstration here. As you can see, these cobalt, these blue-colored elements are the metals. The vast majority of the periodic table are metallic. Over here, these bronze-ish looking ones, these are the nonmetals. Please notice that does include hydrogen. Excuse me. And then here, there's just a few elements on what we call this little staircase. It's actually called that. The staircase divides the periodic table from the metallic side over on the left and the non-metallic side over on the right. And these elements that are sitting on the staircase are known as metalloids or semi-metals because they're kind of like metals and kind of like non-metals. So, for example, metals are typically said to be shiny or have luster. Metals are typically known to be malleable, able to hammer into sheets, or ductile, being able to draw out into a thin wire. They have high melting points, good conductors of heat and electricity. Non-metals are pretty much the opposite of that. They are brittle, so they will shatter if you take a hammer to it. They have low conductivity and conduction of electricity and heat. Metalloids are kind of in between, so they might have properties of metals and nonmetals all at the same time. But again, the biggest thing to note from here is the vast majority, the left side of the periodic table, including these bottom two rows, these are the metals. Over here on the right, we have the nonmetals, and then we need to also include hydrogen in that characterization of the nonmetals. So I went over a couple of these, but just briefly take a moment to look over these properties because you might have a question or two in which we ask you, for example, you have an unknown material and it is dull and it is brittle and it has a low melting point. Therefore, you could conclude what type of element would this possibly be? And you could say it's a non-metal based on the properties of non-metals. So do take a moment to make sure that you know that these different properties exist. That way you know what those terms and definitions, especially things like malleability and ductility, are going to be things that you're probably going to see on an upcoming test. Some other terms and definitions that we definitely need to go over, those are groups versus periods. Groups are also known as families, and these are the vertical up and down columns on the periodic table. There are a total of 18 groups on the periodic table. If we count all these columns, we would have 1 all the way up to 18 over here. Then we have the periods, the horizontal left to right rows of the periodic table, in which there are 7. Please take notice of the fact that there's only 7 rows of the periodic table. A common misconception is that students look at what we call the lanthanide, this row right here starting with lanthanum, and actinide series starting with actinium, this row here. They seem to believe that this is row number 8 and this is row number 9. As it turns out, Lanthanide series, if we look at the atomic numbers, we have element number 56 followed by 57. So this entire row is actually part of period number 6. On a similar note, we have radium here, and it is element number 88 versus actinium, which is 89. So that means that this row here is part of period 7. Now, why do we even kind of copy and paste those two rows below the periodic table? Well, simply put, if we didn't, this is what the periodic table would look like. And I don't know about you, but this periodic table is just a little bit too long and is not going to necessarily fit too well on a piece of paper. So that's why we use the condensed version that we use nowadays. Now, a couple of other things that you need to know about the periodic table is that the reason why groups are sometimes called families is because just like if you have any siblings, you probably have a lot of similar physical characteristics. You look the same. In a similar fashion, groups, also known as families, the elements in these groups exhibit very similar chemical and physical properties. And so that's why we also call them families. In fact, there are some groups that have such unique properties that we have given them special names. You do need to make sure that you know the different names of these special groups. For example, here in group number 1, excluding hydrogen, we have the alkali metals. That's why we exclude hydrogen, because we've just learned that hydrogen is non-metallic. So the alkali metals. This is followed by the alkaline earth metals in group number 2. Very similar name, just a little bit different in terms of properties. Some properties that make this particular group very unique. They are metals, but we can cut them with something like a butter knife. That's pretty odd, considering most metals we think are very sturdy, very hard substances. But these substances, you can simply take a butter knife and cut them. They kind of have a texture like Play-Doh does almost. These metals are so reactive that you will not find them in their elemental states in nature. They're going to be bound in some chemical bond to another element. In fact, if you did want to purify something like sodium, an alkali metal, you would then have to store it in oil or something like argon atmospheric conditions to get it to not react, because it certainly does want to react. In fact, the alkali metals are the most reactive metals on the entirety of the periodic table. Groups 3 through 12 are the transition metals. Now, as we're going to discover later in this unit, transition metals are very, very unique. They have their own set of rules, and they're just pretty out there. So we'll come back to them, but we're not too worried about those. The halogens is the next group that you definitely need to know. Any of the colored groups are the ones that you'll want to know. The boron, carbon, nitrogen, and oxygen family, not too important, but any of these colored ones are. So the halogens. Halogen means salt former. In fact, the halogens are the most reactive non-metals on the periodic table, fluorine being the most reactive one, as we'll discover in, I believe, 3-3. Then finally, we have the noble gases, which does include helium. The noble gases are unique insofar as they are unreactive or inert, which again means unreactive. They have what is known as a stable valence shell, and due to that reasoning, they don't want to react with other things, and that's why we call them the noble gases. They're kind of their own unique categorization of elements. The lanthanide and actinide series simply make up our intertransition metals. Now, a couple other things that you might have picked up on with this periodic table that I need to make sure that you are aware of are what are known as the representative elements. And the representative elements are a certain number of groups on the periodic table. You can quickly identify a group of representative elements if they have a next to the group number. So instead of just calling this group 1, sometimes it's called group 1A. Instead of this, for example, being called group 14, we call it 4A. And any of these that have an A in their group name are called representative elements. So that would include group 1, 2, and then groups 13 through 18. All of those elements are representative elements. Now, the reason why that's important is because the reason why these elements in the same group have similar chemical and physical properties in the first place is because they have the same number of valence electrons. What is a valence electron? So a valence electron is an electron found in the highest energy level of an atom's orbits. That is to say, the outermost energy level possible for that particular element. So for example, all of the elements in the halogen family have 7 valence electrons. Hence the numbering system, 7A. It matches. For example, the alkaline earth metals. All of the alkaline earth metals have a grand total of 2 valence electrons. Hence why the group number is 2A. The transition elements, which would also include the intertransition elements, usually have a letter B with their group number. So for example, this would be 1B, 2B, etc. But the reason why we don't really focus on those is because, again, the representative elements are important because the group number for their representative group, it matches the number of valence electrons that those elements have. And since the number of valence electrons is the same for all of those elements in that group, that is the reason why they have those similar chemical and physical properties. Now, some common, because of the fact that all of these elements in the same group have the same number of valence electrons, when these elements ionize, they will form the same type of ion. For example, all elements out of group 1 are going to form a positive 1 cation due to the fact that they all have 1 valence electron. On a similar note, group 16 elements, we discovered that group 16 is also known as 6A, meaning that all elements in group 16 have 6 valence electrons. And since all of them have 6 valence electrons, they will all, when they ionize, form a negative 2 ion. This is because all of these things, all these atoms, when they ionize, are trying to form a stable octet, which is 8 valence electrons in their outermost energy level. And since they have the same number of valence electrons, they're going to do the same process to make it so that they have that full valence shell. And so it's a good idea to make sure that you know the charges of these particular groups, because we're going to ask you questions like, what is the charge of a fluoride ion? And so you need to recognize, since that fluorine, the atom fluorine is in group 17 or 7A, it's always going to have a negative 1 charge. So make sure that you know these common ions. There's a couple of transition metals here that are very important to know. I would say the more important ones to know besides these are zinc with a positive 2 charge, cadmium also with a positive 2 charge, and silver with a +1 charge. The rest are not as important, but make sure that you at least know those 3. If it helps at all, what I've typically told students is if you don't think you're going to be able to remember those specific charges, most students remember aluminum and the fact that aluminum, being that it's in group 3A, has a positive 3 charge. And if we look at this kind of diagonal line, starting with aluminum, then zinc, then silver, we go in descending order, +3, +2, and then +1 with silver. You just got to remember cadmium, seeing that it's in the same group as zinc, it has a positive 2 charge. Now, we are eventually going to get into some quantum mechanics and things like electron configuration. And one of the things that you're going to need to know for that is the blocks of the periodic table. Again, this periodic table was not put together haphazardly. It was designed in a very specific manner. If you ever wanted to know the number, the highest energy level electrons, which orbital those electrons are going to be in, you could find where that atom is positioned on the table and know, based on the block that it's in, what that highest energy level orbital is going to be. So for example, these first 2 columns make up what we call the S block. Please do take note that helium actually is a part of the S block. The transition elements here all make up the D block. We have the P block over here with group 13 going through group 18. And then the F block here is the lanthanide and actinide series down here. So make sure that you know that, because when we get into electron configuration, all this is going to start coming together and make a little bit more sense as we start to see some of those things there. Last thing to mention with the periodic table is there are 7 elements on the periodic table that, when they exist in their purest elemental form, that is to say they are not bound chemically in a compound with any other different atom, then they are going to exist in pairs, hence the word diatomic. The prefix di means 2, so 2 atoms. So there are 7 of these elements, and you have to have them memorized because we're going to have these types of questions and these elements on those questions. The 7 elements that are diatomic by nature are bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. I usually write them in this order because when you do, it kind of spells this funny German almost sounding name called Brinkelhoff. Brinkelhoff. And so if you just remember that funny name, you might be able to remember the 7 diatomic elements. If that doesn't help you, as it turns out, if we look at where those elements are positioned, here are the 7 diatomics. We have nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And if we look, we can trace an outline of a 7, and there's 7 diatomic elements. The only downside to this method is you cannot forget that poor old hydrogen is included in that group. He's just all the way over here. So again, with these diatomic elements, guys, it's a simple matter of you just simply got to get them memorized. The sooner the better. That way you don't mess up any of those questions on future assessments. With that said, that's the entirety of VLO 3-1. If you have any questions, you can seek me out or any of your chemistry teachers. We're more than happy to help you out. And just make sure to reach out so we can then, make sure that you're getting all the help that you need. Until then, I hope you have a good one and have a fantastic day.